In the previous video, we looked at which trig substitution to use in which situation, so this slide is just a quick reminder of those situations. Let's now continue and take a look at a few more examples.
Consider the integral of 1 over x square root x squared plus 9 dx. Now in the previous slide we saw that x equal 3 tan theta will be a suitable substitution, and we will restrict theta to the open interval minus pi over 2 to pi over 2, as on this interval 3 tan theta ranges from minus infinity to positive infinity, and the sec squared function is positive on this interval. We will also remember that we will use the squared identity that tan squared theta plus 1 is equal to sec squared theta. Now, if x is equal to 3 tan theta, then dx d theta is 3 sec squared theta, and that therefore dx is 3 sec squared theta d theta. And now we are ready for our substitution. So x can be substituted by 3 tan theta and dx by 3 sec squared theta d theta. Now if I take a look at the square root of 3 tan theta squared plus 9, if I square 3 tan theta, I'll get 9 tan squared theta plus 9. So 9 is a common factor inside my square root. If I take out the 9 as a common factor, I'm left with a tan squared theta plus 1, which we know is equal to sec squared theta. And the square root of 9 can be taken out as the constant 1 over 3. Now, technically, the square root of sec squared theta is equal to the absolute value of sec theta, but on our chosen interval, sec theta is positive, and therefore the square root of sec squared theta is just equal to sec theta. We can simplify our fraction, and if we simplify this further, sec theta is 1 over cos theta, and tan theta is sine over cos theta. So if we simplify this, I will be left with 1 over sine theta, which is equal to cosec theta. Now when I integrate a cosec theta, so the integral of cosec theta is negative ln of the absolute value of cosec theta plus cot theta plus a constant. Remember that we need to rewrite our answer in terms of x. We know that x is equal to 3 tan theta, so tan theta is x over 3. To find expressions for cosec theta and cot theta in terms of x, we're going to look again at our right-angled triangle with reference angle theta. Now tan theta equals x over 3 is the opposite over the adjacent, and therefore my opposite is x and my adjacent is 3. And using Pythagoras, I can calculate that my hypotenuse is equal to the square root of x squared plus 9. Now cosec theta, which is the reciprocal of sine theta, is hypotenuse over opposite, which is therefore the square root of x squared plus 9 over x. Cot theta is the adjacent over the opposite, which is 3 over x. So my final answer is minus a third ln. Cosec is now the square root of x squared plus 9 over x, and cot theta 3 over x plus my constant. If we consider the integral of 1 over the square root of x squared minus 4 dx, we realize that the suitable substitution is let x equal to sec theta, where theta is restricted to the first and the third quadrants. We will also remember that we'll need to use the squared identity that sec squared theta minus 1 is equal to tan squared theta. Now if x is equal to 2 sec theta, then dx d theta is 2 sec theta tan theta, and that implies that dx is 2 sec theta tan theta d theta. Now we are ready for our substitution. So x can be substituted by 2 sec theta and dx by 2 sec theta tan theta d theta. When I square 2 sec theta, it gives me 4 sec squared theta, and 4 is therefore a common factor inside my square root. If I take the 4 outside of the square root as 2 and cancel it with the 2 in the numerator, then sec squared theta minus 1 in my square root can become tan squared theta. Now the square root of tan squared theta again is equal to the absolute value of tan theta, but since tan is positive on the first and the third quadrant, this can simply simplify to tan theta. Cancelling out my tan thetas leave me with the integral of sec theta, which integrate as the ln of sec theta plus tan theta plus c. To rewrite my answer in terms of x, I must remember that x is 2 sec theta, which implies that sec theta is equal to x over 2, which is the hypotenuse over the adjacent. So my hypotenuse is x and my adjacent is 2, and using Pythagoras, I can calculate that the opposite is equal to the square root of x squared minus 4. Since tan theta is the opposite over the adjacent, it means that tan theta can be substituted by square root of x squared minus 4 over 2. So my final answer is the ln of, now sec can be substituted by x, and tan by the square root of x squared minus 4 over 2 plus c. In this final example, we're going to look at the definite integral of the square root of 16 minus x squared dx between minus 4 and 4. Now the suitable trig substitution will be let x equal 4 sine theta on the interval minus pi over 2 to pi over 2. So if x is equal to 4 sine theta, then dx d theta is 4 cos theta, and dx is 4 cos theta d theta. So x can be substituted by 4 sine theta and dx by 4 cos theta d theta. However, we must also substitute our boundaries. Now, if I look at my graph and I look at x equal to negative 4, I realize that theta is equal to negative pi over 2. When x is equal to 4, theta is equal to pi over 2. When I square 4 sine theta, it gives me 16 sine squared theta. So 16 is a common factor inside the square root and can be taken out as a 4 to give me the integral of 4 times square root 1 minus sine squared theta times 4 cos theta d theta. 1 minus sine squared theta, of course, is equal to cos squared theta, and 4 times 4, which is 16, can be taken out as a constant. Again, the square root of cosine squared theta is equal to the absolute value of cosine theta, but since cosine theta is always positive on the interval between minus pi over 2 and pi over 2, the absolute value of cosine theta is just cos theta, and my integral simplifies to 16 times the integral of cos squared theta d theta. To integrate a cos squared theta, we use the power reducing formula, a half 1 plus cos 2 theta d theta. And we can now integrate this to give me 8 theta plus a half sine 2 theta, but this must be evaluated between minus pi over 2 and pi over 2. Now the good news is we don't have to take our answer back to x. We must simply substitute in the boundaries pi over 2 and minus pi over 2. So when I substitute my boundaries, it will give me 8 times bracket pi over 2 plus a half sine 2 times pi over 2, close the bracket, minus, open a new bracket, minus pi over 2 plus half sine 2 times negative pi over 2, close the bracket. If I simplify the first bracket, sine of 2 times pi over 2 is sine of pi, which is 0. So my first bracket simplifies to pi over 2, and my second bracket simplifies to negative pi over 2. So I have pi over 2 minus negative pi over 2, which is pi over 2 plus pi over 2, which gives me a final answer of 8 pi. Now it's easy to confirm this answer. If I look at the square root of 16 minus x squared, that is a semicircle with radius 4. And evaluating the integral between minus 4 and 4 means I need to calculate the area of the semicircle. Using geometric formulas, the area is a half of pi r squared, which is a half of pi times 4 squared, which is half of 16 pi, which is 8 pi.